When studying conditional probability, we're dealing with events such as A and B, which are not independent. This means that the probability of one event occurring is affected by whether or not the other event has occurred. And the first formula we learn is the conditional probability formula, which states the following. The probability of an event A occurring given event B has occurred is equal to the probability of event A and B occurring divided by the probability of event B occurring. And I'll go ahead and box that formula. This is the conditional probability formula. Do make a note of it. And just to be clear, the event A followed by a vertical bar followed by B is the event of A occurring given B has already occurred. And when we write this, A is known as the event, that is, the event whose probability we're trying to calculate, and B is known as the hypothesis. That's the event that has already occurred, or the event that we're assuming has already occurred. Let's spend a minute to see how this formula actually works, or how we actually get to this formula. For that, I'm going to quickly draw a Venn diagram with two events A and B. So something looking like this. I have a universal set, which I'll call capital U, inside of which I have the set A, corresponding to event A, as well as the set B, corresponding to event B. Since we know that event B has occurred, when calculating the probability of event A occurring given B has occurred, the fact that event B has occurred allows us to reduce the size of this universal set and restrict it entirely to the set B. Indeed, since we know that event B has occurred, the only outcomes we need to consider are the outcomes inside the set B that I'm currently hatching in green. And now, since we're restricted to the set B, the only way that event A can occur is if we're dealing with an element that's inside the intersection of the two sets A and B. Consequently, the probability of event A occurring given B has occurred is equal to the number of elements inside the set A and B, that's the intersection of the two sets, divided by the number of elements inside the set B. And in fact, we could stop there and say that this is the formula for conditional probabilities. But for the sake of writing this formula solely in terms of probabilities and not in terms of number of elements, we can go ahead and state that this is equal to the number of elements inside set A and B divided by the number of elements inside set U, that's a universal set, all of which is being divided by the number of elements inside set B divided by the number of elements inside the universal set U. And you can go ahead and check, but this fraction is indeed equal to the one above it. Now at the top of this fraction, we can see that this corresponds to the probability of event A and B occurring. Indeed, that's the probability of event A and B. On the other hand, at the bottom of the fraction, we can see that we're dealing with the probability of event B occurring. We can therefore write that this equals to the probability of event A and B occurring divided by the probability of event B occurring. And that's the probability of event A occurring given B has occurred, which is the same formula we stated at the beginning of this tutorial. On top of that, we'll often rearrange this formula to find a formula for the probability of event A and B occurring. Indeed, we can rearrange this formula to state that the probability of A and B occurring equals to the probability of event A occurring given B has occurred times the probability of event B occurring. And I'll go ahead and box that formula as well. This is sometimes referred to as the second conditional probability formula or as the multiplicative property formula. So I'll just write that multiplicative property formula. And as we'll be seeing when working with the total probability formula or Bayes formula, this multiplicative property formula will become very useful, so do make a note of it. It's also worth pointing out that if events A and B are independent, in other words, if we weren't dealing with conditional probabilities at all, then the probability of the event A occurring given B has occurred is simply equal to the probability of A occurring. And that's characteristic of independent events. In other words, whether or not event B has occurred would have absolutely no effect on the likelihood of event A occurring. And so if ever two events A and B are independent, the multiplicative property formula, in other words the probability of A and B occurring, turns into the following. The probability of A and B equals to the probability of A given B, but as we've just seen, that would simply equal to the probability of A, so I'll write that. That's probability of A times the probability of B. So I'll write that as well, times the probability of B. And you have no doubt come across this formula before for independent events. And the difference between this formula in gray and the one I boxed in red here truly highlights what we're dealing with here. We're dealing with conditional probability, in which the occurrence of one event, in this case the hypothesis B, has an impact on the likelihood of the event A occurring. And there we go. Do make a note of the two formulae that we've seen here, as we'll definitely be needing them in the tutorials to come. For now though, that's it for this tutorial.